Welcome everybody. Welcome everybody to our Gamma seminar. This is our last seminar before Christmas. So let me wish you happy holidays. And today we have the pleasure to guest Julia Lange, who is going to talk about, Julia, I cannot do the title.
Oh,
but
yeah.
it was an introduction to Courant algebroids. Yeah, okay. So Julia, thank you for accepting our invitation and preparing the talk. So the floor is yours. Please go ahead.
Oh, yeah. Thanks for introducing me. So, yeah, as the title says, I'm going to introduce you to one of few structures I'm going to introduce are Courant algebroids, and this is our main focus, along with Dirac structures, which are very closely related to these. So it's not going to be anything special, like groundbreaking, but I'm going just to get you familiar with these structures. So treat this like some kind of lecture and to get known to different mathematical structures. So first I'm going to start with introducing what Lie algebroid is. So if we are given a vector bundle from E to M, and we are given a Lie bracket on the sections on E, and some map which goes from E to the tangent bundle of M. This row is called the anchor map, and we have this relation. So basically, Lie algebroid is a triple consisted of a vector bundle, a Lie bracket, and this row anchor map, which satisfies the following condition you can see here. The most trivial example of Lie algebroid is just a simple tangent bundle like this. And then our anchor map becomes just the identity on tangent bundle. Because of course, you know, this relation, whenever we have two vector fields with a function, it just goes down to the bracket of two vector fields plus x acting on f times the other vector field. Okay, so this is the simplest example of Lie algebroid. We can also think of the Lie algebroid structure on a cotangent bundle. So let me introduce you to that. So now our bundle E would be, our vector space would be cotangent bundle, cotangent space, and we are our bundle is a cotangent bundle, and we define the bracket, the Lie bracket in the following form. Okay, so you can clearly see this is antisymmetric. Yeah, you can also check that this satisfies the Jacobi identity. What is important, of course, we have to assume that lambda is a Poisson bivector. Okay, so then the Jacobi identity is satisfied. And the anchor map is just defined by this lambda in the following way, like this, okay? In this case, you can verify that that this condition for a Lie algebroid is satisfied. So let me just like rewrite this to prove it. Okay, so whenever we have two one forms, and we use the formula for our Lie bracket, we just write it like that. Okay, and now the f goes outside of this formula. And here we can rewrite this term as in two other terms. And here the f goes outside of the Lie derivative. Okay, so we can see that what we obtain is basically this plus this term. So here, this is our anchor map in this case. Okay. So yeah, that is a standard example of a Lie algebroid structure on a cotangent bundle. Now I want to introduce you to some generalization of this kind of structure, which is called the Courant algebroid. So once again, we are considering some vector bundle. And right now, we are also given a bracket, but it's not in general skew-symmetric, okay? So it's not a Lie bracket at all. We are also equipped with a symmetric bilinear form. And as before, we are given this anchor map, which goes from E to Tm. So you can see there are several conditions which needs to be satisfied, which define Courant algebroid, okay? You can show that the condition number 2 is just a result of conditions 1 and 3, but first, but we usually write it to clarify things, okay? And yes, like I said, the bracket is not skew-symmetric, since from the condition number 5, we could write that the bracket of two elements, two sections on E, is given by minus the bracket when we change the terms, plus 2 times this derivation map E1, E2. Okay, this derivation map, it goes from the functions on our manifold M to the sections of on our vector space E. Okay, and it is defined in terms of our bilinear form and the anchor map and exterior derivative.
Julia?
Yeah.
It's even simpler than that, because, you know, if it could be antisymmetric in 5, the left-hand side would be always 0, yeah? But when you pick up the bracket with a section with itself, one knows that the module of it will be different from 0 in general, yeah? So
yeah, in other words, if this D derivation map equals 0, then we are dealing with skew-symmetric bracket, okay? And it turns out, in other words, if D is 0, then this Courant algebroid becomes the Lie algebroid, which I mentioned before, right? So, yes. So now it turns out that whenever the Courant algebroid is exact, which means that if we are given the sequence of this form, here we have so if this sequence is exact, we call that the Courant algebroid is exact, and then we can identify E with the so-called generalized tangent bundle or point tracking bundle. In some references, you can see that name for this bundle. So this is basically a Whitney sum of tangent space and cotangent space, okay? Yeah, so we can, further on, we will basically consider these types of bundles where E is just this generalized tangent bundle. Okay, so now let's us build a current algebroid structure on this bundle. So here, the choice of anchor map would be just the projection on the first term of our elements in a generalized tangent bundle. So whenever we are given some vector field in one form, the row just gives us this vector field. Okay, we define the bilinear form in the following way. So this is just the contraction with we contract x with xi prime and x prime with xi. In many different, like if you read the literature, sometimes you can see like 1.5 before this, in front of this term. Well, there are many different definitions and they always differ by some fractions, okay? So you need to be careful. It just goes to different type of defining structures, okay? And also, we define the Dorfman bracket, which will be this current bracket, in the following way. So you can see this Dorfman bracket is clearly not antisymmetric. Yeah. Some authors prefer to define this bracket as a symmetric one, like they define it in the following way. So if we are given two elements in our generalized tangent bundle, they alternatively define it as this. Okay, so this bracket is antisymmetric. However, whenever I've occurred, like I happen to see this type of brackets while defining what we will later proceed to the current structures, the Dirac structures. Yeah, this bracket okay, maybe let me leave it for later, because I need to first discuss Dirac structures, okay? So assume we have this current algebroid structure on our generalized tangent bundle. And now I would like to define Dirac structures, which are related to current algebroids. Okay, so we call a Dirac structure a subbundle D of E relative to our bilinear form, such that the sections of this bundle are closed with respect to our current bracket, which means basically this. Okay, you can say then that this condition, if we require D to be maximally isotropic, it means that D is Lagrangian, so that the space perpendicular orthogonal space to D is equal to D. And in result, the rank of D is just equal to the dimension M, okay? So whenever I occurred that people would use the bracket, which is antisymmetric, they would define Dirac structures irrelevantly of current algebroids. Because this bracket, you can see, this antisymmetric bracket would fail to satisfy the first condition. Okay, but it doesn't really matter, because when we are speaking of Dirac structures, it turns out that on the sections of on Dirac structures, like the sections on D, if we calculate the current bracket, it's antisymmetric on them. So then these two defined brackets would agree on the sections on our Dirac structure, and it doesn't make a difference. However, I would prefer to use the bracket, which is specifically called the Dorfman bracket, which I defined here, okay? It has a few advantages, like it's less complicated for sure, so it's easier for calculations and so on, right? Okay. So what is important here, like I've mentioned, when we take the sections on our Dirac structure, D, our bracket becomes antisymmetric. And then it satisfies the Jacobi identity, so we actually obtain a Lie algebroid structure on the bundle DM. Okay? Now let me give you some examples, basic examples of Dirac structures. So assume that we are given some bivector field on M, and then we consider the graph of this map related to our bivector, like lambda sharp, yeah. So our bundle L lambda would consist of all cotangent, like one forms, and the image of these forms through lambda. Okay, it turns out that this bundle is a Dirac structure if and only if lambda is a Poisson bivector. Okay, in other words, the Schouten bracket of this lambda vanishes. Okay, this is equivalent for saying that lambda is a Poisson bivector. Okay, I would like to make a remark that if lambda is any bivector, then we have that the orthogonal of L lambda equals L lambda. However, for lambda not being Poisson, it fails that the sections on L lambda, so we can write that so we have sections on L lambda. This belongs to the sections of L lambda if and only if lambda is Poisson, okay? Because we have two conditions for Dirac structures, that it's Lagrangian and it's closed under the Courant bracket, okay? So the second condition fails if we are not given the Poisson structure. Okay. Alternatively, we can consider another example if we are given a differential two form, and then consider the bundle L omega, which is given by vector fields, plus the image on X through this map related to our two form omega, which goes from Tm to cotangent space. And once again, it turns out that this bundle is a Dirac structure if and only if omega is presymplectic, which means that the exterior derivative of this omega vanishes. Was there any question? Okay. And once again, if we are given any two form, then L omega is Lagrangian. However, this closure under the Courant bracket is not satisfied unless omega is not presymplectic. So of course, for symplectic form, it works as well. Yeah. One question we may ask is, if we are given a Dirac structure, right, on our generalized cotangent tangent bundle, we would like to ask whether it comes from Poisson structure or not. Well, it's enough to, like, if we go to the example I gave before, if where L is Dirac structure, we can say that L equals L lambda if and only if the intersection of L with Tm equals 0. In other words, it means that in L there cannot be elements of the form x plus like the one form like term is 0. Okay, because you have to remember that this intersection is in generalized tangent bundle. Okay, and similarly here we can say that L equals L omega if L is Dirac, if and only if the intersection of L with cotangent space equals 0. Okay. Okay. Here's another example, very specific. So we consider M to be equal to real space of dimension 3. Okay, so we are given the coordinates x, y, z, and let us define the bundle spanned by the 3 elements. So the rank of this bundle is 3, which is equal to the dimension of M. Okay, so there is a chance it could be a Dirac structure. Yeah, and we can verify that this bundle is indeed Lagrangian. Yeah, and these sections are, the sections of L are close with respect to our brackets we defined before. And also we may verify that indeed the intersection of this bundle L with cotangent space is equal to 0. So then we know that we can write L as the image of some bivector field. Bivector field, which is a Poisson bivector, okay? And indeed, we find this lambda to be in the following form. Okay, so this should be here. Yeah, so simple calculations shows that it really works. However, we can see that this bivector is singular at z equals 0. Well, our Dirac structure given on L is smooth actually. But what happens here, even though our Poisson bivector is singular at z equals 0, it just means that at z equals 0, this Dirac structure cannot be written as in, like, we cannot, it's not true that L equals L lambda at z equals 0, okay? Because at this point, we have that L, intersection of L with tangent space is not equal to 0, okay? Because this element vanishes and we are just given the element of this form which belongs to Tm. So the intersection would not be 0. Okay, do you have any questions, comments?
Julia,
yeah.
One comment. You have talked about the relation of Dirac structures with presymplectic and Poisson manifolds. Could you comment on the relation of Dirac structure with other geometric structures?
Other? Oh, yeah. I will. You mean specifically twisted Poisson?
No, I was more in general, because what I meant is that you can relate also Dirac structure with Jacobi, for example. You can do it also with, in particular, with contact manifolds. But you have to guess, you have to assume that the Dirac structure is constructed in all the manifolds. For example, in the case of Jacobi, it's not the image of a bivector field, but it's the image of a bivector field with a third time vector field, yeah, that does not vanish, that it will take the role of the red vector field, the Jacobi structure content. So what I mean is that you have studied the most emblematic, the most important geometric structure related to Dirac structures. But the point is that you could also study the relation with other ones, okay? For example, as I said, Jacobi or contact are the easiest one. That's the comment.
Yeah, but in this talk, I wanted to focus on Poisson, which are. I just wanted to mention at the end the relationship that we can consider something more general, like almost Poisson manifolds.
Yes, sure, but it was just a comment because all people lately are focused on contact. Yeah.
Oh, okay, okay.
But I fully understand what you mean and what is your aim. And
okay, I didn't think about including this part in my talk. So, yeah. Okay. Another example would be considering some regular distribution in Tm. And we would define the bundle L as just the direct sum of this regular distribution and its annihilator. So the annihilator is just included in cotangent space. And we can easily verify that L is indeed Lagrangian subbundle, and the integrability condition is satisfied if and only if our distribution is involutive. So it is tangent to the leaves of regular foliation. And yeah, this is important that we may view Dirac structures just as regular foliations. Yeah, which are presymplectic foliations. There is a one-to-one correspondence. So when we have non-degenerate Poisson structures, we can speak of symplectic structures. And we are given Poisson structures, this corresponds to symplectic foliation. And Dirac structures similarly correspond to presymplectic foliations. Now I would like to talk a little bit about gauge transformations, because they actually give some notions to generalize our considerations of Poisson structures to almost Poisson structures. In particular, the structures which I work on currently, which are called twisted Poisson structures. So let's consider the action of the group of closed two forms on M on our generalized tangent space. So this action is given by that element X alpha goes to X, and the term in cotangent space becomes, there is added additional term of contraction of our field with this two form B. So we can verify that this, this map preserves our bilinear symmetric form and also the bracket. So in other words, the gauge transformations of Dirac structures take us to another Dirac structures. However, we would have to redefine our Courant bracket. Yeah, in the following way. So we define the new Courant bracket with this addition of minus exterior derivative of two form B. So it consists of the original bracket minus dB contracted with vector fields X and Y. So in other words, we can write this formula. So yeah. Okay, so this is the morphism of our Dirac structures, right? So when we observe that, we can also consider more generalized structures. Like one of them is twisted Poisson structure, which consists of additional three form phi. So twisted Poisson structures are such structures that the Schouten bracket of lambda does not vanish, but is related to the 3-form phi in the following way. Okay. So yeah, and this phi is a closed 3-form. So now we could redefine the Dorfman bracket by adding the term related to this phi in the following way. Okay, so it would turn out that this newly defined bracket yeah, it would also be a Courant bracket, and we would have a Dirac structure being an image of, like, being the graph of minus lambda in this case, whenever lambda is now not the Poisson bracket, but is, yeah, it's not a Poisson bracket, but now we can also obtain a Dirac structure by taking the graph of this minus lambda. Okay. Yeah. Now I would like to discuss some further actions we can do with Dirac structures. For example, the reduction, which is of course very important in physics and all applications. So we can consider whenever we are given some Dirac structure. Okay, so D is Dirac structure. And if we consider some isotropic distribution, okay, isotropic distribution. So we have that it's included in the orthogonal, okay, and it is a part of our generalized cotangent tangent bundle. So if we construct a bundle in this way, so we take the intersection with the orthogonal, and then we add this distribution, it turns out that this is Lagrangian, okay? Because if we take the orthogonal of it, simple calculations shows that we are given this, and now yeah. However, D is a Dirac structure, so D orthogonal equals to D. Sorry. So we obtain this, but this equals to our distribution since it's isotropic, okay? So we get the original bundle. So we can say it's Lagrangian. However, the sections on this bundle would not be in general closed under the Courant bracket. However, there are several cases we might consider because yeah, they lead to closure under the bracket. Like we can choose the distribution H in Tm, and we set this distribution nu be the annihilator of H. And then it turns out that this bundle, the stretched Dirac structure, becomes also a Dirac structure. So there's a closure under the Courant bracket of the sections on D nu. And then it turns out that we can reduce the Dirac structure, this Dirac structure, stretched Dirac structure, to a submanifold N, where N is just any leaf of the foliation which is induced by our distribution H. Okay. Another example would be, once again, we consider some distribution in Tm, which is integrable, and then our Dirac structure stretched bundle induces a Dirac structure on the M over our distribution H. And this can be further reduced to this space. Okay, and we consider here N to be a leaf of another integrable distribution, which is a part of Tm. Okay, so in this process, this is actually something I'm working on currently, but in terms of the twisted Poisson structures I mentioned before, and the question we try to answer are whenever we are dealing with a Dirac structure at the beginning, which comes from this twisted Poisson structure or wherever, the question is whether we end up with the Dirac structure which also inherits a similar properties, right? Or we can also reverse this question. If we end up with something which can be related to twisted or in general almost Poisson structure, does it come from the Dirac structure which is related to similar analogous structure? Okay, so yeah, these are the this is the bibliography. I strictly recommend this one. Yeah, you can get to know with many aspects of Dirac structures here. Yeah. And if you want to read something about the reduction I've been talking in the last slide, I would strictly recommend this one. Okay, so thank you for your attention.
Thank you, Julia, for your presentation.
I finished much earlier than I thought, but maybe...
Yeah, it's not a problem, Julia. You know, also we made not much questions because, well, from my point of view, it was very clear. Yeah, sometimes we talk before about the talks, and I see that the main notions are clear. I don't say anything. So, okay. So, do you have any question, remark, comment?
I think that Adam has, but
yes,
he cannot turn.
Say.
But he's muted.
But the last reference you were talking about this by Bursten,
yeah,
definitely suggests that it has some interesting applications in geometric and topological methods for quantum field theory. So do you have any physical example or something like that? Because during your talk you also mentioned the gauge transformations for Dirac structures. So
yeah, exactly.
So I would like to see an example because it looks like something that can be used to understand really deep structures in physics. So,
well, there are not too many like very specific physical examples, which are, I don't know.
Physical, something even from string theories from physics.
But
like,
Adam, which kind of example do you want? I mean, about Dirac structure, it's plenty of them in applications in systems with constraints, and there are quantum systems with them. You can describe the Dirac brackets by means of them. Then there are a couple of examples in electronics that were described also by means of Dirac structures. Indeed, they were pretty much famous, yeah, in something like 15, 20 years ago. But what kind of other application you have in mind? In field theory or in
field theory, basically?
Yeah, because well, I'm not familiar with the examples particularly pertaining to quantum field theory. Mm,
In my case, I mean, what Julia did, it was just an introduction with the simple examples, okay? But for example, the brackets introduced, the Courant one, okay, the canonical one, let's say this way, for this Courant with the splitting, yeah? They are all more general than that. For example, you have Courant algebroids, which are not the generalized algebroid, okay? It is something like the tangent with the exterior product of the cotangent, okay? And then you have also Courant brackets, and these Courant brackets can be used to study field theories, okay? So this is one case of that, but I think I know that it can be done. Yeah, there are some relations, for example, with multisymplectic. In these and previous talks, we will talk about it. But if I tell you the truth, I know that it can be done, that there are some applications, but I didn't check the applications. And all this story about the Dirac structure, the first was by Patera, I think, by Weinstein. They all appear in quantum field theories. Is that if I remember correctly? So, but I never check it out, truly speaking. Okay. Interested. I could check it out. I could give you something, but
there are no specific examples in this reference I was talking about. I think that the title is pretty misleading. Like
a little bit, yeah.
It's a clickbait, you know.
This is indeed maybe a good remark about the talk, that the title can be misleading.
It's very technical, this paper. Maybe he provides some comments about it, but
wait,
not
Ruben wants to say
examples.
something. He said that Dirac structures appear in the infinite dimensional setting of classical field theories. Okay, I didn't know that. It's a pity that you don't have a microphone. Ruben, could you develop that? Say something more.
You're asking me? Sorry.
No, I'm talking about Ruben,
okay.
because he has no microphone. He doesn't. It does not work, his microphone, and he's writing on the chat.
Oh, okay.
So the thing is that he talks about the infinite dimensional setting of classical field theories. Okay, so I don't know why, but I would like to know. So if you have anything else to talk about that, it would be very welcome. It seems that there is no comment so far. Yeah. In the singular setting, usually brackets are obtained through Dirac. Yeah, but you don't have to go to the infinite dimensional setting. That's, I mean, it happens all the time. I mean, Dirac structures can be used to singular setting, but I mean, what I didn't know was the infinite dimensional setting. I don't know what you mean exactly. Let us do this way. Ruben, if you have any reference, could you paste it in the chat about what you mean in infinite dimensional setting? It would be good for everyone. Because maybe I know what you are talking about, but the language is, you talk in such a manner that I don't know what you mean. Or we don't know what you mean. Well, so we can wait for Ruben, but meanwhile, is there any other question or remark?
Yeah, I have a question. Can you go back to this twisted Poisson or
Here?
yeah, exactly. I mean, as I understand, did I understand correctly that you can also consider? I mean, what's okay? Wait, let me.
What's the point?
Yeah,
well,
when you just take this twisted thing on in a particular case, which is the group, is it any connection between phi and, for instance, Maurer-Cartan form? I mean, in this particular case?
Like we can write that if phi equals d omega, for example. Because I wrote this phi in terms of phi, right? In terms of lambda, the bivector field.
Yeah, and if you take, I mean, because you take the like arbitrary manifold M, so with the Poisson structure.
No, it's not Poisson structure. It's some other structure because lambda is not Poisson here.
Yeah, I mean, yeah, okay, yeah, fair enough. And can you, so if you take the particular example, if you can take such one, when M is at T star, I mean, T star G, for instance, I mean, can you define something like that? I mean, when I don't know if you make sense here,
if we have what?
In particular example, for instance, T star T, I mean, okay, never mind. I just need to think about it.
Okay. Like we can always construct, like consider the bundle having any Lie group, we can consider this, right?
Yeah, exactly. This is what I was thinking about. And can you define for such an example the twisted? What would be the twisted structure here?
Well, it would be formed in terms of this bilinear form and the bracket. Okay, it would be something like this, with some, I don't know, term like 1/3. Like I'm just guessing, but it also always depends on many things, how you define things, but it will be proportional to something like that. Okay, this free-form term.
Okay.
Okay, because in fact, yeah, exactly.
Yeah, it is right. This is what we did in our work. Yeah, I mean, it was,
but what is important, if the dimension of our manifold is less than 3, am I saying it right?
Yeah, because afterwards it will be so, and things like, I mean, it's been trivial. Well, like, trivial. You know. By the way, we work on it in our work, but this is idea by Einstein and Patera, I guess. They wrote in the paper, so it's not ours. And this structure is also related with other types of quasi-Poisson, yeah, manifold. That is what she said. This girl, I don't remember her name. It was Maxen, like let me check, because I think it was.
We have a message on our chat with the
reference. Because Ruben found the word, the book by Dorfman, that he said that is in that book. I will have to take a look. It was Maxen, no. It was Anna Balibanos.
Yeah.
About this.
Yeah, she was talking about this.
Yeah, sure. Thank you, Ruben. I will check it. Now, I don't really remember that book, really. So maybe I miss it. So it's a good thing to know. Thank you.
Oh, I would like to mention that in March, I would be talking specifically about the reductions on twisted Poisson manifolds. So you can treat this like an introduction to it, because probably I will not have enough time to, to provide the examples and slowly introduce you to these topics.
Indeed, this is the idea of this to introduce
Yeah.
different structures, and I mean it's very basic. Is the most introductory things about it.
Mhm.
Okay, so is there any question, remark? Okay, so thank you for all your questions and remarks. It's been very interesting. I will check what Ruben shared, by Dorfman, because I didn't remind it, truly speaking. And thank you all for your participations. Have a good time with your family. Have a rest, and Merry Christmas. See you next year.
Yeah. You too. Merry Christmas and Happy New Year.